So I'm going to tell you about KPZ fluctuations in finite volume and how these statistics can be expressed in terms of integrals on Riemann surfaces. So first I will give some introduction about KPZ fluctuations and discretized version, which is the asymmetric exclusion process. Then I will tell you how the vector ansatz for the totally asymmetric model can be nicely expressed in terms of Riemann surface. Then I will show you how a fluctuation of the totally asymmetric exclusion process can indeed be expressed in terms of integrals on this Riemann surface. And then eventually, taking the infinite genus limit of the Riemann surface, we end up in the KPZ region. So KPZ fluctuation in one dimension. So initially it was introduced to describe interface growth. So you have a one-dimensional interface that grows between two phases. And the KPZ fluctuation gives you the universal statistics of the height of the interface. But over the years, KPZ fluctuation has been, it has been noticed that KPZ fluctuation appears in many other situations. For example, so driven particle system, where the field now is the current of particles, or directed polymers in random media, where the field is the free energy of the polymer. Also, one-dimensional classical and quantum fluid with a few conservation laws where KPZ fluctuation describe some normal hydrodynamic modes. More recently, you have also some kind of random unitary dynamics where you apply gates randomly into a quantum system, where the entanglement entropy is shown to fluctuate like the KPZ height function, and also in some disordered systems, the conductance of the system, at least the logarithm of the conductance, is also described by KPZ. So it appears in quite many different contexts. So you have some universal statistics that are the same in all these contexts. You have universal scaling functions, not just universal exponents. One can compute this scaling function because in the time evolution of the probabilities in KPZ are actually integrable. So KPZ comes from the Kardar-Marizan equation, which was introduced as an equation describing the height of an interface between a stable phase and metastable phase. So the stable phase grows steadily, and so it grows in this way. So the time derivative of the height of the interface at position x and time t is given by a surface tension term, some noise, and plus some nonlinear term, which is related to the curvature of the interface. So here I will be, KPZ fluctuation has been investigated mainly on an infinite system, so x belongs to the set of real numbers. But here I will be mainly interested in finite volume setting, in particular with periodic boundary conditions. So I have a system of size L, let's set L equal to 1 maybe. But one can also look at open systems in particular, where you fix the slope of the interface at both boundaries. So this KPZ equation, the solution is some very rough function. So, which means that the nonlinear term here is not very well defined. in some sense, you multiply some distribution. So to make sense of this equation, it's actually quite hard, but it has been done rather recently. In particular, Martin Heyer got the Fields Medal for mainly managing to describe a proper normalization scheme which gives this, which gives a proper meaning to the KPZ equation. So here, I have 4 parameters for my KPZ equation, so 3 parameters in the equation, plus 1 parameter which is the system size. So one can always rescale the parameter, rescale time, space, and the rate of the interface. So we are only left with 1 parameter. So let's just say I put all the parameters equal to 1, except of the term, except because for the coefficient in front of the nonlinear term. And now, so the statistics of the rate will depend on this parameter lambda in a non-trivial way. In particular, there are 2 interesting limits, which are in some sense fixed point of the renormalization group. So lambda equal to 0, which for which we don't have the nonlinear term, so it corresponds to the fluctuation of an interface at equilibrium. It's called the Edwards-Wilkinson fixed point. It's repulsive in terms of normalization group. It has a dynamical exponent z equal to, which means that the correlation length grows to, grows with time like t to the power 1 over z, so square root of t. And so the other fixed point is the KPZ fixed point. So yes, in this KPZ business, you have 2 things that we call KPZ. The KPZ equation, which depend on this parameter lambda, and the KPZ fixed point, which is the thing that we'll be interested in here, which is the limit lambda going to infinity, which is an attractive fixed point with dynamical exponent z equal to 3/2, and which corresponds to a truly irreversible revolution. And so, so we have this fixed point for the KPZ equation, but because of universality, these, like for equilibrium critical phenomena, at the fixed point we have universality, so it means that the correlation function has the same form for any model in the universality class, but also we have something stronger here. In fact, the flow between Edwards-Wilkinson and KPZ, so the statistic with fixed lambda, is also thought to be universal here. But so in this talk, as I said, I will be mainly interested in periodic boundary condition and the KPZ fixed point lambda going to infinity. Okay, so now let me introduce the symmetric exclusion process, which here is understood as some discretized version of the KPZ equation. So the asymmetric exclusion process, so it's a system, one-dimensional systems of particles, which O asymmetrically, so it's an exclusion process, so you have at most 1 particle per site, and the particle O with rate 1 to the right, and with rate Q to the left, and let's say we take periodic boundary conditions. So it's a continuous time Markov process. I call L the number of sites and the number of particles. And so this model can be in fact mapped rather easily to an interface growth model in the following way. So to each site which is occupied by a particle, you associate a portion of interface that goes down. To each empty site, you associate a portion of interface that goes up. So it gives you some interface. And you see that the dynamics of the particle model translates for the 8 model in terms of particle, some squares that drop into local minima of the interface with rate 1, and evaporate from the maximum of the interface with like Q. So in this sense, AZ is really a model of Brownian interface, and it will be in the KPZ university details. And so you see from this mapping that the height of the interface in the height model is the same thing, more or less, as the current of particle in the particle system. Okay, and so this model, this exclusion process is actually integrable, and in fact it's closely related to the x-axis spin chain. So for instance, consider the total time-integrated current, so the total number of particles that are posed anywhere in the system of time t, where one can show that the generating function of this time-integrated current is given, it evolves in time by this operator M of gamma, which is similar to the Hamiltonian of an x-axis spin chain with twisted boundary conditions. The twist here makes the matrix non-Hermitian. And so it's x-axis, the anisotropy of the x-axis spin chain delta is just the square root of Q plus 1 over square root of Q divided by 2, so it's always larger than Okay, so now how is KPZ related to this exclusion process? Well, you have to scale the asymmetry, so 1 minus Q as 1 over square root of the system side, with some parameter lambda, which is the same parameter lambda as before, so the coefficient in front of the nonlinear term of KPZ. And so, in principle, in this scaling, this 8 here of the interface goes to the KPZ8, has the same statistics of the KPZ8 in the scaling limit. And in particular, for the two fixed points of the Edwards-Wilkinson and the KPZ fixed point. So the Edwards-Wilkinson fixed point, so lambda equal to 0, you see that it corresponds to the symmetric exclusion process, Q equal 1, where the particle open both sides to the same rate. And the KPZ fixed point, on the other hand, where you want to take lambda going to infinity here. So in particular, you see that if you don't take 1 minus Q to scale as 1 over square root 12, you just take Q different from 1, it should be in the KPZ fixed point, and you can as well take Q equal to 0, where the calculations are much easier. In order to study the KPZ fixed point, you can just study the totally asymmetric exclusion process, so Q equal to 0, which corresponds for the spin chain to an anisotropy delta going to infinity. So this is for the typical fluctuation of the A, which will be described by KPZ. In fact, in this KPZ scaling, it sits between two regimes. One, phase-separated regime, where you consider large deviation of the current, where the current is much lower than the typical current. So in this case, where to have a very small current, it generates in the system a jam, where all the particles are together and the rest of the system is almost empty. So you get a phase-separated regime. And on the other hand, if you look at large deviations where the current is very large, where the particles want to be as far as each other as possible, and Karevsky and Schutz have shown in some sense that you have conformal invariance in this region. So I won't be interested in this large deviation regime here, but I will be here mainly interested in the typical fluctuation that are described by KPZ. Okay, so more precisely, so I consider KPZ fluctuation in finite volume, the KPZ fixed point in finite volume. So I will have a random field H of position and time with periodic boundary conditions and some initial conditions. So I mean, as usual, the calculation can be made only for specific initial condition, simple initial condition, particular or flat initial condition, or sharp wedge initial condition where you have an infinitely sharp wedge, or stationary initial condition where the initial height is a random Brownian ring. And so the object that we'll be interested in will be the general endpoint statistics of the height, so the probability that the height at position x1 times t1 is equal to something, and I mean, I will have endpoints and distinct points to consider. So how to do this? Well, there are several ways. So if you start with TAZEP, as I will do, one thing you can do is you expand all your formula in terms of beta eigensets. So all your formula, I mean, formulas like this. You have this exponential t times this matrix m of gamma, which is the Hamiltonian of x exists. So you can expand this in terms of beta eigensets, and more generally for the endpoint function, you can do something similar. So you end up with some formula that depends on the solutions of beta equations. And then from this formula, you want to take the KPZ scaling limit, so large system size, large number of particles. And actually this can be done by using some generalization of the Euler-Maclaurin formula. But this is actually extremely tedious calculations. So here I will be using a different approach, much more recent, which consists first, before doing the asymptotics, to rewrite everything in terms of integrals on Riemann surfaces. And I mean, these Riemann surfaces come from analytic continuation of the different eigenstats. So I will end up with some rather nice and compact formula for the probability of the KPZ8. And the structure of this formula in terms of Riemann surface will essentially go through in the KPZ scaling limit. So in the KPZ scaling limit, we have also integrals over some non-compact Riemann surface. So this is the approach I will be presenting you here. So there are other approaches. We can also start from TAZEP, but instead of expanding over eigensets, you can write an integral formula for the propagator. So this was done by Beck-Mu. And I mean, the advantage of this approach is that it's more rigorous. Fortunately, it gives rather complicated formula, much more complicated formula than from the Riemann surface approach. So this, I mean, these two approaches, you consider TAZEP, so discretization of the model. In principle, you can also try to work into the continuum by using what is called the replica solution of the KPZ equation, where the KPZ equation is mapped to an attractive delta Postgad. So with this method, it has not been possible so far to compute the probability. There are only some preliminary works by Brunel and Derrida about some large deviation function, but in principle, this approach should also give the same scaling function. Okay, so now I will consider the beta ansatz for the totally asymmetric exclusion process, and I will show you how it can be formulated in terms of Riemann surfaces. So on the left here, you have the usual formulas for beta ansatz for the asymmetric exclusion process. So it's essentially the same formulas as for the x-axis spin chain. So you have your usual beta equations. The eigenvalue is a simple sum over the beta root. The eigenvectors are given by sum over permutations. and for instance, the normalization of the second vector is given by the Gaussian determinant. Turns out that for the totally asymmetric case, so Q equal to 0, these formulas simplify usually. So in particular, the eigenvectors are given by a determinant. Also, the Gaussian determinant, which is just a determinant usually, it can be computed, in fact, completely explicitly, just a sum over the beta roots. And most importantly, the beta equation simplified greatly. So if you take Q equal to 0 here, what we are just remove this, but here Q equal to 0, so here you just have yj to the power n, and in the denominator you have the product of the yk. So if you introduce now this parameter c equal to exponential L gamma times this product, the beta equation actually I write in this simple way. So you see that the beta equation for TAZ has a kind of mean field structure in the sense that for AZ each beta root is coupled to every other beta root in a complicated way, while for TAZ each beta root is coupled to the other one only through this parameter c. And so the appearance of this parameter c is what will give us the Riemann surface I told you already about. In particular, we'll see that symmetric function of beta roots will be interpreted as meromorphic function on the Riemann surface. Okay, so I start with the beta equation, so written in terms of this parameter c. So the beta equation are just this equal to 0 for y equal to a beta root yj. So I'm interested in the solution of this equation for y. I fixed the value of c, and I want the L solution of y of this equation. So you see that if you put this term on the right and take the absolute value, the solution live on this curve in the complex plane, which are some transforms of generalizations of some classical curves called Cassini-Oval, which are given by this, and which have the following shape. So if there is a value c star, which is some explicit function of the system side and the number of particles, such as if c is larger than c star, this Cassini-Oval has a single connected component. And if c is smaller than c star, it has two connected components. So, okay, c star, you see that it will correspond to a branch point. I want to consider the solution in y of this equation as function of the variable c. I'm interested in the analyticity of this function in terms of the variable c. So we see that the value c star, which is some negative number, will correspond to a branch point of this function y of c. And you have also other branch points, so you have c equal to infinity, where all the beta roots converge to the same point, which is also a branch point, and also c equal to 0, where some beta roots go to 0, some go to infinity. So it means that these functions yj of c have potentially three branch points, 0, infinity, and c star, which all are on the negative real axis. So it means that this function must be analytic in c minus the negative real axis. So I have L function, y1 up to yn of c, which are analytic on this. And now, what happens when, so you have the cut of this function. And so what happens when I cross this cut? Well, so the function yj will be transformed into another function yk, into another solution of this equation. So you have you have two operators that gives you a permutation of how the beta roots are transformed when you cross this cut or when you cross the other cut. And this gives you some permutation group, which is the full symmetric group if and only if the system size and the number of particles are co-prime, which will be important in the following. In fact, for technical reasons, at some point I will restrict to this setting, which is in fact enough to take the KPZ scaling limit anyway. Yes, and so here, this picture, so it represents the beta roots. So I mean, the blue and red curve represent this Cassini oval, and the dots are the beta roots corresponding to a value of C, which is positive. And the domain which are delineated by the black curve are just the image of the complex plane minus the cut by the function yj. So you have all these domains that are together here. Okay, so in this slide I will define some Riemann surface corresponding to a single beta root. So this is not what I will need in the following. I will need the Riemann surface for symmetric function of n beta roots, but I mean to introduce some notation, I will first consider the one beta root case. So I have this L function y1 up to yl, and by analytic continuation, you go from one of the domain of the yj to another domain when you cross the cuts. So if you now glue together all the domain of the definition of all the function yj, you end up with a Riemann surface, which is obtained just by gluing together the domains along the cost minus infinity C star and C star 0, according to how analytic continuation is made for the yj. So it gives us a first Riemann surface that I call R1, the R1 meaning Riemann surface for one beta root, and a point of this Riemann surface, it's what? Well, it's a complex number C, which is the value of C, and an index J between 1 and L, which indexes the L sheets of the Riemann surface. And in particular, the various function yj give a meromorphic function on this Riemann surface by this following formula. Y at a point C j is just yj of C. And this by construction is a meromorphic function on this Riemann surface R1. Yes, so I said that the points of the Riemann surface can be written that way. So all these points are distinct except for some identification corresponding to the branch points. So in particular, the point 0 on the sheet 1 is equal to 0 on the sheet 2 equal to 0 on the sheet n. You have several identifications which correspond to the points where several curves meet. So you have the identification between all the points coming from this sector, this sector, this sector, this sector here. Same here, you have this 4 sector that is the same point, and also for the point at infinity. Okay, so what is this Riemann surface R1? Well, in fact, one can see that easily from the algebraic curve, but let's do it naively for a moment. So I will want to compute the genus of this Riemann surface, the genus being the number of holes in the Riemann surface. So to do this, I consider the following covering map. So that sends my Riemann surface to the complex plane, in fact, to complex plane plus infinity, which is called the Riemann sphere, where the infinity is only in a consistent way. So this covering map is just defined in this way. I take the point Cj of my element surface and I just keep the C. So it's a conformal, holomorphic mapping from my element surface to the sphere. And now, if you have a covering map between two Riemann surfaces, well, you have a relation between the genus of the first Riemann surface and the genus of the second Riemann surface. So, in general, if you take two compact Riemann surfaces, connected compact Riemann surfaces, M and N, and a covering map of DLD, DLD meaning that each point on N has D antecedents, each generic point of N has D antecedents on M. Then the Riemann-Lewis formula gives this. So the genus of M is D times the genus of N minus 1. It's 1 plus a sum over the ramification points of the covering map on the Riemann surface M. So a ramification point is what? So take a small circle around some points on the Riemann surface M. So this small circle is sent to a closed curve on the Riemann surface M. And the winding number, if the winding number of this curve around the image of the point is 1, well, this is not a ramification point. Otherwise, the winding number is equal to the ramification index. And so, this formula, which may look a bit complicated, in fact, it's just some easy consequence of the regular characteristic formula. So that if you take a graph, well, 2 minus 2 times the genus is the number of vertices minus the number of edges plus the number of faces of your graph. And so you use this for a graph on the Riemann surface M, which links all the ramification points, and you end up rather easily with this form. Okay, so now if you use this this Riemann-Lewis formula, so the ramification points here of my covering map phi 1 are just these points here actually. And the ramification indices are just the numbers. So here, for instance, this point has a ramification index n, this one minus n, this one l, this one 2. And if you put all the numbers here, you end up with the fact that this Riemann surface has a genus really equal to 0. And it's known that there is a single Riemann surface of genus 0, which is the Riemann sphere, to isomorphism of Riemann surfaces. So this Riemann surface R1 is just the sphere. In fact, it can be already seen from the algebraic curve. So here I solve in terms of the variable y. I could have solved in terms of the variable c. And here you see you don't have any branch points, so it's defined on the sphere. So on this diagram, you see that if you add the points at infinity, you just get the sphere. Okay. But this is just the Riemann surface corresponding to a single beta root. Now, the formulas, the beta Andas formula, remind you, you have such kind of formula, which are all actually symmetric functions of n beta roots. So now I have to understand what is the Riemann surface on which symmetric function of n beta roots. Because an eigensets of TZ just correspond to a choice of n solution of this equation among the L possible. So let's consider a symmetric function of n variable. Let's say a meromorphic function in all the variables to not introduce additional branch cuts. And I want to know how this thing is transformed when I cross the cuts of the function yj. So when I cross the cut 0 C star or C star infinity. And what happened? Well, yj1 is transformed according to its transformation across the code. Same from Y2 to Ygen. So you end up with another, after processing the code, these J1 up to Jn, which are distinct numbers between 1 and L, give you another permutation after crossing the code. And well, the Riemann surface on which this thing lives is just indexed by all the possible choices of these integrals. So the point of the Riemann surface is just C plus the set J equal J1 to J. So actually, by doing this analytic conciliation, we may not always. The Riemann surface may have several connected components. It's possible that you can't go from one set J to another set J by analytic conciliation, but it just means that the Riemann surface has several connected components. And one can show it the case if the system size and the number of particles are not confined. So here, for instance, you have the number of connected components for several values of L and N, and it's equal to 1 only when L and N are not confined. And so you can also compute the genus of this Riemann surface. So when you have several connected components, just the sum of the genus of each connected component. And you can compute this again using the Riemann-Lewis formula, using this covering map here. That's N, C, J, just to C. And if you do that, I've not found a particularly nice formula for each value of L and N, but at least for small values of L and N, you can compute it. And so for a small n or n close to L, you have a genus 0, so a sphere. But when L and N grow with, let's say, a fixed ratio, then the genus grows as well and goes to infinity exponentially fast, actually, with L and N. Okay. Okay, so that's it for this Riemann surface. And now I will study the H fluctuations of KPZ. And I will show you that these H fluctuations can be expressed in terms of integrals on this Riemann surface. We will get some function of the Riemann surface that will be what is called traced over this covering map, which means that we will sum over just all the sheets of this covering. So all the sets. Okay, so this is the formula I will end up with, which is actually rather simple for this complicated object. Okay, so I want to compute the generating function of the KPZ plate. So I want to compute something like this. So you have the 8 at position I and time. No, sorry, so this is the one. No, so in the end, I want to compute this. So I have n, small n points corresponding to times TL and sites IL, and you want to compute the generating function. So as I said earlier, the one-point generating function is given in terms of this matrix, which is similar to the Hamiltonian of the extinction chain. And since this is a Markov process, by the Markov property, you can, the evolution between T1 and T2, which was also given by the same metric, and you have a formula for the generating function that involves this matrix M for some fugacity gamma, which is related to the gamma here. And this is decorated by some operators that just sum the position of the particle from given site I, and which is used to get the position, to fix the position of the bit. And so, yes, you have to, the dynamics tells you how the 8 evolves in time, but you need to start with some initial 8. And so the only meaningful choice is this choice. So Ni is the occupation number of the system at site I, so it's equal to 1 if there's a particle at site I, and 0 if the site is empty. And on a periodic system, well, this will give you a periodic function which corresponds to this mapping between the particle system and the height. Okay, so we start with this formula, and as I said, I want to expand this into the eigenstates of n. So you end up with some formula. Actually, so you end up with some formula, and well, you want to rewrite everything in terms of the solution of the basic equation, and in particular, when you want to compute all these scalar products, but it turns out that all of them have simple expression in terms of the beta root. So the Godin determinant I've already showed you, but you have also other scalar products which can be computed rather easily using the Sylvain determinant. So I won't enter the detail, but you end up with some formula, which is well, not particularly illuminating, but it's an exact formula for the generating function. So you sum over n sets of beta equation. You have the initial condition that appears in this determinant. You have this thing that comes from scalar products. You have your Godin determinant here in the denominator. Some formula. Now, what do you want to do with this formula? Well, ultimately, I'm interested in the KPZ scaling. So I like the large L and N asymptotics of this formula. But as I told you earlier, trying to do it from this formula, it's quite tedious because you have to, use some two-dimensional Euler Maclaurin asymptotics with some nested singularities. So it's not very nice. You end up with an ugly formula in the end. So a better approach that I am going to describe is to write this in terms of the Riemann surface, in terms of integral on the Riemann surface. And it turns out that the good object is not the generating function, it's the corresponding probability. So, okay, you start with this formula and you try to rewrite the probability of the height. So the generating function is the same as before. You just change a variable called GL equal to exponential gamma L. Well, by definition, you sum over all possible values of the 8 increments. Probability that the 8 is equal to initial 8 plus some increment, and you have these values here. And so you see that the probability, you can extract it by taking residues. So we end up with an expression for the probability with some integrals over this GL, or some integrals over the gamma L. This fugacity gamma L, the same. But now these variable GL are not the good variable we want. The good variable we want is these parameters C in terms of which Riemann surfaces are expressed. So you want to make this change of variables. Since C was exponential gamma times the product of the beta. And it turns out that you can compute the Jacobian. And the nice thing is that this Jacobian is essentially equal to the Godin determinant. So you see that this Jacobian will cancel this term in the denominator, which is nice because this term it has it gives poles at not arbitrary point, but at complicated points. Because just a sum, so the sum can vanish. some points, not the product where the poles are simple, but it turns out that this change of variable eliminates this nested pole. Okay, so we end up with a formula, and now, all the beta roots are now a function of this variable c, so we end up with formula that live on the Riemann surface. But it turns out that everything can be expressed in a much simpler way. If all the products I have, I try to rewrite them as exponential of integrals on the Riemann surface. It turns out that this way, I end up with simple formula. Okay, and this is the result. So I restrict to the case where L and N are co-prime, so that I have a single connected component, so I can go from any point to any other point on my Riemann surface on some path. And here I write for the formula for just this specific initial condition. So this is the full probability of the 8 at n distinct points. So you get some contours integral, some sum over the sheets of the Riemann surface corresponding to each of the points. And you get some integral. And you see that this integrand has an extremely nice expression. So on the numerator, you get some exponential of integral between a point O. The point O on my Riemann surface is this point. So the point of coordinate 0 on the sheets j equal the integrals between 1 and n. And I integrate on my Riemann surface between this point O to the point CLGL on which I am integrating. And so I am integrating what? Some meromorphic differential on this Riemann surface, which is built from these two functions mu and eta, which are very simple functions of the beta roots. Okay, so this is the numerator, and the denominator, you have also an integral over a path gamma between 0 and 1 in such a way that CLB plus the sheet on the Riemann surface and CL plus 1B with the corresponding sheet goes from OO to CLGL, CL plus 1, GL plus 1. So, all this is a rather simple object which involves these two meromorphic functions on the Riemann surface. Okay, so you are integrating this meromorphic differential on the Riemann surface, and integrating meromorphic differentials on the Riemann surface, it's like integrating meromorphic function. You can have logarithms, so they may not be analytic, but thanks to the exponential, in fact, everything becomes analytic because, in the beginning, I only had a symmetric function of the beta roots, so these are functions which are well defined on the Riemann surface, and this can be understood by the fact that the corresponding residues are integers, so when you take the exponential, they don't give anything, and the periods, which correspond to integrals over some handle on the Riemann surface, are also integral multiplier of 2i pi, so the integrals do not depend on the paths on the Riemann surface. Okay, so here we have a function that live on the Riemann surface, but here we are integrating just on the complex plane, or on the sphere if you want. So how do you go from functions on the Riemann surface to an integral just on the complex plane? Well, you have this sum in between, which is called the trace of the covering map, which sends you a point Cj on the Riemann surface to a point C on the sphere. And it's known that if you take the trace of a covering map of a function living on the higher Riemann surface, it gives you a meromorphic function on the lower Riemann surface. So for instance, think of the function exponential of square root of C, so which has branch cuts, so but it can be defined as an analytic function on a two-sheeted Riemann surface. Now, if you consider the trace of the covering map that it sends you this point to the sphere, while the analytic continuation of exponential of square root of c is exponential minus square root of c, and if you take the trace, so you sum these two contributions, well, it's actually an analytic function in the complex plane. So the branch cuts compensate in some sense. And the last remark, so this formula, it involves the position of, the sites at which I'm computing the rate. You can notice that this position do not appear on the right-hand side. Doesn't mean that this formula doesn't depend on this position. Actually, the dependency is either in the fact that you want the 8 here minus the initial 8 to be an integer. But since the initial 8s are not integers, you have a dependency, in fact, on the I, which is either in the formula. Okay, so you can, so this was for a special initial condition. For a general initial condition, well, you have to insert, this function depends only on the first variable, which is a symmetric function of the beta rows, but in knowledge it cannot be written in simple way as exponential of an integral, but some specific initial condition can be written in a simpler way, like this. Okay, so now, so this was a result for the totally asymmetric exponential process with a finite number of states and a finite number of particles. Now I want to take the larger scaling limit, which corresponds to a limit of infinite genus for the Riemann surface. Yes, so this limit is a bit complicated. So you have, in principle, a sum over all the sheets, which are sets, finite sets of n elements between 1 and f. But actually, in the scaling limit, only some sets will contribute in this scaling limit, only sets which correspond to particle excitation over the fundamental eigenset, which corresponds to the set J equal 1 to n. And so you make holds and excitation on both sides of this Fermi sheet, and these are the only set that will contribute in the scaling limit. And so when you take the scaling limit, this function mu, the function mu, which appears everywhere in this formula, you can show in a simple way by residue that this function converges actually to a polylogarithm function. Give you some derivative of this function. So it means that the Riemann surface that you end up with in the KPZ scaling limit is in fact the Riemann surface on which this polylogarithm function is, and which is an infinite genus Riemann surface. Okay, so I started with a Riemann surface which had a single connected component, but it turns out that in the scaling limit you have some several points of the Riemann surface which become very far from each other, and in the scaling limit they become in some sense isolated, so you have to sum over various species, so over various connected components. component of this Riemann surface R KPZ. You get some formulas which are essentially the same formulas as for LAPTh. So you get now the probability of the KPZ in the scaling limit, so as position x1, t1 up to xn, tn. And you get, as before, a sum over all the sheets of the Riemann surface, an integral on the complex plane, and you have the same kind of expression as before, so exponential of integral on the Riemann surface. And you get some extra factor here, which is a bit ugly, but comes from the singularities, some singularities that appear in the KPZ scaling limit near this point, O, from which I started my integrals in the finite scale. Okay, so this is some formula, but so something that was noticed very recently is that these formulas have an interpretation in terms of tau function of some classical integrable system. So to be specific, let's consider the flat initial condition. So I start with an initial 8 h equal to 0, flat, and let's look just at the one-point distribution. So in this case, so the probability of the 8, well, it's also written in terms of the sum over all the sheets of the Riemann surface, and integral also on the complex plane. But it turns out that the sum over all the sheets can be written in terms of the Fredholm determinant. Well, this Fredholm determinant is it's this. So you have this function, I mean, this integral that calls this tau of x is given by this determinant plus something very better. And this determinant, this Fredholm determinant, has this curve. Now, if you know a bit about soliton solution of the KdV equation, you will notice that this is in fact n soliton solution with n going to infinity of the KdV equation, the Korteweg-de-Vries equation, which is a classical integrable partial differential equation. And I mean, we don't have really a good explanation of why this is the case, why KdV appears in some sense hidden in KPZ. And in fact, very recently, this was extended to other kind of initial condition by Beck and Liu, where they showed that for this initial condition, you get the same kind of structure, but now tau is related to not the KdV equation, but the Kazancham equation, so the natural two-dimensional generalization of KdV, which is also an integrable partial differential equation. Also, around the same point, so this was for I mean, the finite volume KPZ, but also on the infinite volume KPZ, it turns out that the probability can also be described in terms of so-called tau function for KPZ, for KdV and the KP equation. So this is something which was completely unexpected, and we don't really have a good explanation of this appearance of this equation at the moment. Okay, so I'll skip this. I mean, so KPZ in finite volume, when you recover the infinite volume at short time, actually, and the infinite volume, the statistics of the height is given by some trace-equilibrium distribution, so we can recover them. And in the other side, in the long time limit, well, you get some large deviations. Okay, let's keep this. I mentioned some. Should be share here. So as I said earlier, KPZ is in some sense at the edge of conformally invariant regime. So in the conformally invariant regime, the beta roots organize themselves into perfect strings, which are completely distorted in the KPZ regime. Now, if you look at the one particle Hall spectrum of your model, so you get something like this. So for KPZ, so I mean, this is the same thing as for a Littinger liquid. So for a Littinger liquid, you get a spectrum which is 1 over L, I mean gaps which are of order 1 over L everywhere. It turns out that for KPZ, you have different scalings. So you have 1 over L plus power 3½ here, the 3½ being the dynamical exponent of KPZ, and different exponents here, so that for KPZ, this term where you send some quasi-particle from one end to Fermi C to the other end, in fact, do not contribute. So this would be interesting to understand how this, how you go from the conformal regime to the KPZ regime, and how these exponents change between the Littinger exponent to the KPZ exponent. So another direction. So here I talk mainly about periodic boundary condition, but you can also do some things about the open boundary condition, where you put some values of the slope at both boundaries. And recently, with my PhD student, Ulysse Gaudreau, we managed to get, by studying the spectrum, the Riemann surface corresponding to this case, by starting either from large deviation results which were known, or from new Bethe equations which were obtained in this case. And also, an outstanding question is the crossover between Edwards-Wilkinson and KPZ, which would require to consider AZ with, an asymmetry between two. Okay, so I finished. So I have described you Bethe ansatz for Tazel in terms of Riemann surfaces. I've showed you that in the infinite genus limit, where you get some Riemann surface in the KPZ scaling limit, and the probabilities of the 8 have simple expression have integrals on the corresponding Riemann surface. And well, we have an unexpected appearance of solid length from KP and KDB in this problem, but we don't know why. Okay, thank you. Questions?
Yes, I just want to be sure that I understood the stages of the solution that you had in terms of this Li 5 by 2 function, this polygon function. So you have the solution which essentially both contains the typical fluctuations, say the Tracy-Rhythm type fluctuations, and also the large deviations. So is it correct to say that your formula actually contains all these regimes? So it's a bit surprising because, surprising in the sense that I see this polylog function. We know that they arrive naturally when you study the large deviations, but it sounds
that this is duality didn't tell both, but yes, you have also the polylog that appear in another regime in KPZ. We don't know why, but it's another regime.
Yeah, it's another regime.
Just about comparison of your result in your formula with integration on Riemann surface and the use of exact propagator. In that case, also you have integration. So, is there
presumably you can reformulate the propagator approach in terms of Riemann surfaces. So they did not do this, but presumably it can be done. Yes. So
you think you can compare?
We can compare the formula. They are equivalent, but since they don't write things in terms of Riemann surface. They have complicated terms, but these complicated terms you can reinterpret them in a simple way in terms of these integrals on Riemann surfaces. But presumably you can, from the start, drive the propagator directly in terms of the Riemann surface. I would guess it should be possible.
Maybe I have a question about in the slides where you present the short time scales. So can you give a bit also more details about how in finite size you recover the KPZ project in short time? And so, or why does it appear?
Yes, so you have a correlation length that goes as t to the power 1/3. When time goes to infinity, what you have such a field, which gives you the Large-Deviation regime in stationary Large-Deviation. That short time, the correlation length is much smaller than the full system size, so essentially it's like you are